This is Chapter 16, Capacitance from Grove's Electronics book. So, what we want to look at is what is capacitance? Well, capacitance is the ability of a dielectric to hold a charge. So, we need to identify what a dielectric is. We will in a second here. So, if we want to look at what first the symbols of a capacitor, we have a fixed capacitor. Basically, a fixed capacitor has, these are two plates here, and in the middle here is called a dielectric. This is called an electrolytic capacitor because it actually has polarity to it. It has a positive and negative. The negative is always to the little hump down below, and the positive is usually the line that goes across. And the variable capacitor basically is a symbol for variable capacitor is similar to this one or this one, but it has an arrow through it. So first of all, what is a dielectric? Well, let's look at a capacitor itself and identify the working parts of it. So a capacitor itself has basically two main parts to it. It has two plates and it has a dielectric. The dielectric is the material which we want to hold the charge. And usually a dielectric is like paper, mica, it could be glass, it could be air, it could be anything. And what happens here is that we want to understand that a dielectric is not going to be conductive. All its purpose is to isolate the two plates, but hold that charge. Is to hold that charge. So in this circuit right here, what we have is a source, a DC source, a path, and we have our capacitor. And we have two plates and a dielectric. In this case, we're going to say our dielectric is air. So when a voltage flows from the battery, the positive to the one side of the plate, the negative to the other side of the plate. What's going to happen is this capacitor is going to equal the full source voltage over here. So what's going to happen is that the dielectrics actually start storing this charge in here. So when the voltage at these plates equal the source voltage, no other current's going to flow on here. This capacitor is fully charged. That's what we call fully charged. That means the dielectric now has a charge in it. So if we disconnect this battery and we put a short right here or put a light here, we can discharge the capacitor and this light will light up because there is a charge on this capacitor. So the two big concepts I want you to understand is the dielectric is an insulator and also the dielectric stores a charge. As mentioned in the schematic above, once this capacitor reaches the source voltage, the dielectric the voltage at the dielectric is going to equal to the source. So if this is 10 volts, the dielectric is going to be 10 volts. There is not going to be any way for current to flow anymore because we have already stored as much as we can on these plates and into the dielectric. So basic fundamentals of a capacitance of a capacitor is its units is farads, and a farad is a very large unit. So Q is equal to a charge, C is equal to capacitance, and V is equal to voltage. Some of the other concepts we want to look at is capacitance usually is measured in microfarads, nanofarads, and picofarads. Micro is 10 to the minus 6, nano is 1 times 10 to the minus 9, and pico is 1 times 10 to the minus 12. The other way we can write these is we can say 1 microfarad, 1 picofarad, let me get that a capital, and whoops, this is 1 nanofarad, sorry, 1 nanofarad, and this is 1 picofarad. So this is nano, this is 10 to the minus 9, this is 10 to the minus 12. This is really small units. These are really small units. So let's look at an example. How much charge is stored in a 3 microfarad capacitor? So if we have a 20 volt applied DC. So we're looking for charge, Q. So Q is equal to C times V. In this case, we have 3 microfarads times 20 volts DC. Gives us 6 times 10 to the negative 5 farads, or 60 microfarads. So basic concepts of a capacitor. Our larger plate is equal to more capacitance, and a thinner plate is equal to less capacitance. So this equation that I actually have here on here is in your book, and we're not going to go into it too deep. But basically what this says is we have capacitance is equal to the dielectric K. Remember, dielectric could be paper, mica, glass, or anything. So there's values that are in your chart. You can also look up these values. Multiplied by the area, the plate area, and the distance between the plates times it by this constant, 8.85 times 10 to the negative 12. So if we have, let's say our dielectric for air is 1, which it is, and our area of our plate is 1 meter, which is quite large. And let's also let's compare it with a area of 2 meters to see what happens. But our distance between the plates are going to stay the same. So the only thing I'm going to change here is my area. So if I use this equation on the top here and I plug in my values, and I plug in some values down here, this is proof that if I do all the math, that I go from 885 picofarads to 1.77 nanofarads. This shows me as my plate area increases, because I go from 1 meter to 2 meters, that my capacitance actually increases. So this is proof that larger plate area does equal larger capacitance. There is a variety of different capacitors that are out there. There is the electrolytic type, and then there's the standard type. But they come in, well, electrolytic is electrolytic. They come in ceramic, they come in film, etc. So the electrolytic is something I want to pay a little more closer attention to. The electrolytic has polarity. If you hook up an electrolytic incorrectly, it will explode. That's because there is a oil-based in there, the material that's in there. And if you hook it up wrong, that oil-based material can start heating up and expands, and that's what causes it to explode on you. So please keep in mind the electrolytic capacitor has polarity, and then you need to pay attention to it. You also want to pay attention to electrolytics are used for large capacitances, such as 1 to, let's say, 6,000 microfarads. I've seen them up to 1 or 2 farads as high. So electrolytics are used mainly for filtering. They're mainly used in filtering. You see them in trying to get rid of noise. You try to get rid of the AC on amplifiers, etc. So film capacitors, if we want to know the value of this film capacitor, we're going to take a look at it. Normally, they'll have a few numbers and a tolerance. So in this case, let's take this as an example. We have 1, 5, 2, and a K. The first two numbers are our digits. The third number is a multiplier. So if we look at the chart, the first 1 through 5 is actually the number of zeros. So if it is a 1, you'll have 1 0, and you have 5, you'll have 5 zeros. This is their multiplier. If it has an 8 or 9, we have to multiply it by 0.01 or 0.1. So please keep that keep that in mind. So our example 152K, the first two numbers are 15, 1 and 5, so this gives 15. Then we add 2 zeros or multiply by 100, gives us 1500 picofarads. If it's 759J, first two numbers are 75, and we multiply it by 0.01 because 9 requires us to multiply by 0.1, gives us 7.5 picofarads. Normally, a capacitor will be in picos or nanos, more or less in picos. We like to convert it over to micros when we can. We don't want too large of a number. So in this case, on the top, your 1500 picos, if we tried to convert it over to micro, we move it over back 6 to the left, it would not make sense. So that's why we're keeping it in picos. But I'll show you an example in a second on when we actually would convert it over. Ceramic, like film, is similar in finding the value. The only thing is on ceramic, a lot of times they do put the value on there. We'll show you an example in a second. So let's say we have a ceramic that has the numbers 102J. Again, 1 and 0, we put the two numbers down, 1 and 0, and then I put the number of zeros down. In this case, gives us 1,000 picofarads. But I can move it back now 3 places to get me to a nano. So this is actually a nanofarad. We could keep it like this, but these are a lot of numbers. Stamping things on a chip and having fewer numbers makes it much more clearer. How about 104? 104. So we have 10, and then we have put 4 zeros down. Well, that's picofarads. So we get almost 100,000 pico. That's too big of a number to even put on a stamp on here. So what we like to do is we'll convert it over. In this case, we can move it over to micro. And what we do is decimals here, we move it back 6 places. 1, 2, 3, 4, 5, 6 gives us 1, 2, 3, 4, 5, 6. Gives us 0.1 micro. This should be 0.1 microfarads. That should be 0.1 microfarads. Again, what you do is move it over 6. So if you have 12, 11, 10, 9, 8, 7, 6. 6 is right there. Well, if it has this example where you have this, you're looking at your capacitor as 0.022 Z. Well, the value is 0.022 microfarads. And if it's written out, and this is going to be in micros, and you see this 5 volts, this means that its max voltage is 5 volts. So let's look at capacitors in parallel and series. So if you have capacitors in parallel, the equation for it is C total is equal to C1 plus C2 plus C3. The voltage across each one of these capacitors, based on parallel laws of parallel, say that it has to be 10 volts. So the voltage is VC1 and VC2 is 10 volts. Capacitance total is equal to 0.1 microfarads plus 2 microfarads equals 2.1 microfarads. So this just shows that capacitors in parallel, the plate area increases. How about capacitors in series? Well, capacitors in series uses this equation. And then if we take a look at a circuit here, ignoring this resistor right here, we have 1 microfarad or 2 microfarad. Well, we could use this equation, or we could use this equation, C1 times C2 over C1 plus C2. And if we do that, we come up with 667 picofarads. So caps in series, the plate area decreases. The other thing is the voltage. Let's say we want to find the voltage across C1, because we have two capacitors it's going to share this voltage. So C2 over C1 plus C2 gives me 6.66 volts. So if I'm looking for C1, 1 microfarad, it's going to be 6.66 volts. So that means this capacitor is going to have the most voltage, and this capacitor is going to have the least voltage. So if you have any questions about capacitance, please feel free to reach out to me, and I'll be more than willing to help you out. Thank you, and have a good day.